Physics is a fundamental science that seeks to understand the universe and its underlying principles. At the heart of physics lies measurement, which is standardized through the International System of Units, known as SI units. These units provide a common framework for scientists and researchers to communicate their findings effectively. The SI system comprises 7 fundamental units that represent the most basic quantities in physics: length, mass, time, electric current, temperature, amount of substance, and luminous intensity. The meter is the unit of length, defined as the distance light travels in a vacuum in a specific fraction of a second. This definition ties the meter to a universal constant, ensuring precision in measurements ranging from everyday distances to astronomical scales. The kilogram is the unit of mass, originally defined as the mass of a liter of water. It is currently defined by a physical artifact, but scientists are transitioning to a definition based on fundamental constants, such as the Planck constant, to enhance accuracy. Time is measured in seconds, defined by the vibrations of cesium atoms, which oscillate at a precise frequency. This atomic definition allows for highly accurate timekeeping, essential for technologies like GPS and scientific experiments. Electric current is measured in amperes, named after André-Marie Ampère. 1 ampere is defined as the flow of 1 coulomb of charge per second, a crucial unit for understanding electrical circuits and electromagnetism. Temperature is measured in kelvins, based on absolute zero, the point at which molecular motion ceases. The Kelvin scale is vital in scientific research, particularly in thermodynamics and quantum mechanics. The amount of substance is measured in moles, representing a specific number of particles, typically atoms or molecules. 1 mole contains approximately 6.022 x 10 to the power of 23 entities, known as Avogadro's number, which is essential in chemistry for quantifying reactions and understanding substance behavior. Luminous intensity is measured in candelas, quantifying the amount of light emitted in a particular direction. This unit is important in fields such as photography, lighting design, and astronomy. In addition to fundamental units, derived units are created by combining these fundamental units to measure more complex quantities. For instance, speed is a derived unit that combines distance and time, measured in meters per second. This unit is commonly used in various applications, such as determining vehicle speeds. Force is another derived unit, measured in newtons. 1 newton is defined as the force required to accelerate 1 kilogram of mass by 1 meter per second squared. This unit is crucial in mechanics, allowing scientists to analyze how objects move and interact. Pressure is measured in pascals, with 1 pascal equal to 1 newton per square meter. This unit is essential in fluid dynamics and meteorology, describing how forces act on surfaces. Energy is measured in joules, another derived unit. 1 joule represents the energy transferred when 1 newton of force moves an object 1 meter. This unit is fundamental in physics, particularly in thermodynamics and mechanics, where energy conservation is a key principle. Power, the rate at which energy is transferred or converted, is measured in watts. 1 watt is equivalent to 1 joule per second. This unit is crucial in electrical engineering and physics, quantifying how much energy devices consume or produce. Understanding SI units is essential for anyone studying physics. They provide a structured framework for conducting experiments, sharing results, and building upon existing knowledge. Without a standardized system of measurement, scientific progress would be inconsistent and chaotic. SI units are used globally, establishing a universal language in science. Whether a physicist in Japan, a chemist in Brazil, or an engineer in Germany, all utilize the same units to describe their work. This consistency fosters collaboration and innovation across disciplines and borders. In summary, SI units, both fundamental and derived, form the backbone of physics. They enable scientists to measure, compare, and understand the universe in a clear and consistent manner. From the smallest particles to the vastness of space, these units help decode the mysteries of the cosmos. Whether measuring the speed of a car, the weight of an apple, or the distance to a distant star, SI units ensure clarity and precision. A solid understanding of these units is crucial for exploring the universe, one measurement at a time. Physics encompasses more than just equations and theories. It is about making sense of the world, and SI units are the key to unlocking that understanding.
Measurement of physical quantities is a fundamental aspect of science and engineering, relying on comparisons with established reference standards known as units. Each measurement consists of a numerical value accompanied by a unit, which provides context and meaning. While the range of physical quantities is extensive, only a limited number of units are necessary due to their interrelationships. This efficiency allows for a coherent system of measurement that can be universally understood and applied. Fundamental units, such as length, mass, and time, serve as the foundation of measurement systems. These base units are essential for expressing a wide variety of physical quantities. Derived units, on the other hand, are formed by combining these base units to represent more complex measurements. For example, speed is expressed as meters per second, meter per second, which combines the base unit of length, meter, with the base unit of time, second. Historically, various systems of measurement have been developed and utilized across different regions and scientific disciplines. Three prominent systems include the centimeter-gram-second (CGS) system, the foot-pound-second (FPS) system, and the meter-kilogram-second (MKS) system. Each of these systems employed distinct base units for measuring length, mass, and time. In the CGS system, the base units were centimeters for length, grams for mass, and seconds for time. This system was widely used in fields such as physics and chemistry, particularly in the early 20th century. The FPS system, commonly used in the United States, relied on feet for length, pounds for mass, and seconds for time. This system has been prevalent in various engineering applications and everyday measurements. The MKS system, which uses meters, kilograms, and seconds, laid the groundwork for the modern measurement system. Today, the internationally accepted system for measurement is the Système International d'Units, abbreviated as SI. The SI system was developed by the Bureau International des Poids et Mesures, BIPM, to provide a standardized framework for scientific and commercial measurements worldwide. The SI was revised in 2018 to enhance its clarity and applicability, ensuring that it meets the needs of contemporary science and technology. One of the key advantages of the SI system is its decimal structure, which simplifies conversions between units. For example, converting from kilometers to meters involves multiplying by 1000, while converting from grams to kilograms requires dividing by 1000. This ease of conversion makes the SI system user-friendly and accessible to a wide range of users, from scientists to engineers to the general public. The SI comprises 7 base units, each representing a fundamental physical quantity. The meter, m, is the SI unit of length, defined by taking the fixed numerical value of the speed of light in a vacuum to be 299,792,458 meters per second. This definition reflects the precision and accuracy that modern science demands. The kilogram is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant, which is set at 6.62607,015 x 10 to the power of minus 34 joule seconds. This definition ties the kilogram to fundamental physical constants, ensuring its stability and reliability over time. The second, S, is the SI unit of time, defined by the fixed numerical value of the cesium frequency, which is the unperturbed ground state hyperfine transition frequency of the cesium-133 atom. This frequency is set at 9,192,631,770 Hz, providing an accurate and reproducible measure of time. In addition to these three fundamental units, the SI system includes several other important units. The ampere, A, is the SI unit of electric current, defined by the fixed numerical value of the elementary charge, which is set at 1.602176634 x 10 to the power of minus 19 coulombs. This definition links electric current to a fundamental property of matter. The Kelvin, K, is the SI unit of thermodynamic temperature, defined by the fixed numerical value of the Boltzmann constant, which is set at 1.380649 x 10 to the power of minus 23 joules per Kelvin. This definition connects temperature to energy, reinforcing the relationship between thermal and physical properties. The mole is the SI unit of the amount of substance, containing exactly 6.02214076 x 10 to the power of 23 elementary entities, known as Avogadro's number. This unit is crucial for quantifying chemical reactions and understanding the behavior of matter at the molecular level. Lastly, the candela, CD, measures luminous intensity in a given direction. It is defined by the fixed numerical value of the luminous efficacy of monochromatic radiation of frequency 540 x 10 to the power of 12 Hz, set at 683 lumens per watt. This definition ensures that measurements of light are consistent and comparable. In summary, the SI system provides a coherent and standardized framework for measurement, ensuring consistency and ease of use across various scientific disciplines. This standardization fosters collaboration and innovation in research and industry worldwide, facilitating advancements in technology, engineering, and scientific discovery. The SI system not only enhances communication among scientists and engineers but also plays a crucial role in everyday life, from the products used in homes to the technologies that drive modern society.
Every measurement inherently contains errors, which necessitates that results reflect the precision of those measurements. This is where significant figures come into play. Significant figures consist of all reliable digits in a measurement, along with the first uncertain digit. Understanding significant figures is crucial for accurately conveying the precision of measurements in scientific and everyday contexts. For instance, consider the period of oscillation of a simple pendulum measured at 1.62 seconds. In this example, the digits 1 and 6 are considered reliable and certain, while the digit 2 is uncertain. Therefore, this measurement has 3 significant figures. Similarly, when measuring the length of an object and reporting it as 287.5 centimeters, this value has 4 significant figures. The digits 2, 8, and 7 are certain, while the digit 5 is uncertain. It is essential to report measurements accurately, as providing more digits than the significant figures can mislead others about the precision of the measurement. The number of significant figures in a measurement is influenced by the least count of the measuring instrument used. The least count refers to the smallest division that can be accurately read on the measuring device. For example, a ruler with millimeter markings can provide more precise measurements than one marked in centimeters. Importantly, changing units does not alter the number of significant figures in a measurement. For instance, a length of 2.308 centimeters retains 4 significant figures when expressed as 0.02308 meters or 23.08 millimeters. The position of the decimal point does not affect the count of significant figures. To better understand significant figures, it is helpful to follow certain rules. First, all non-zero digits are considered significant. For example, in the number 123, all 3 digits are significant. Second, zeros that appear between non-zero digits are also significant. For instance, in the number 205, the 0 is significant because it is sandwiched between the digits 2 and 5. Third, leading zeros in numbers less than 1 are not significant. For example, in the number 0.0045, the zeros before the 4 are not counted as significant figures. Fourth, trailing zeros in a whole number without a decimal point are not significant. For example, the number 1500 has only 2 significant figures, as the trailing zeros do not count. An interesting case arises with trailing zeros in decimal numbers. For instance, the measurement of 4.700 meters indicates precision, as it possesses 4 significant figures. The zeros after the decimal point are significant because they convey the precision of the measurement. If the measurement was simply reported as 4.7 meters, it would imply less precision. When converted to other units, such as 4700 millimeters, it may appear to have fewer significant figures, but it retains 4 significant figures due to the original measurement's precision. To eliminate ambiguity in determining significant figures, scientific notation is highly recommended. This notation expresses numbers in the form of AX10⁻B, where A is a number between 1 and 10, and B is any positive or negative exponent. This format clarifies the number's precision and avoids confusion regarding significant figures. For example, the Earth's diameter can be expressed as 1.28 x 10 to the power of 7 meters, while the diameter of a hydrogen atom can be represented as 1.06 x 10 to the power of -10 meters. This notation clearly illustrates that the Earth is 17 orders of magnitude larger than a hydrogen atom. In scientific notation, all zeros in the base number are significant, which helps prevent confusion regarding trailing zeros. For example, in the scientific notation 4.700 x 10 to the power of 0, the zeros are significant, indicating precision. In contrast, for numbers greater than 1 without a decimal point, trailing zeros are not considered significant. However, trailing zeros in decimal numbers are always significant. For instance, the number 0.1250 has 4 significant figures because the trailing zero indicates precision in the measurement. Additionally, leading zeros before a decimal point in numbers less than 1 are never significant. For example, in the number 0.0032, the leading zeros do not count as significant figures. However, trailing zeros in such numbers are significant, as they indicate the precision of the measurement. It is also important to note that multiplying or dividing factors that are exact have an infinite number of significant digits. For example, if a measurement is defined as exactly 100 centimeters, this number has infinite significant figures. Therefore, when performing calculations, it is essential to recognize the distinction between measured values and exact numbers. In conclusion, understanding significant figures is vital for accurately reporting measurements in both scientific and everyday contexts. By adhering to the rules of significant figures and utilizing scientific notation, clarity and precision can be maintained in measurements. This ensures that the information conveyed is reliable and accurately reflects the precision of the measurement process. Rules for arithmetic operations with significant figures. The result of a calculation involving approximate measured values of quantities, that is values with limited number of significant figures, must reflect the uncertainties in the original measured values. It cannot be more accurate than the original measured values themselves on which the result is based. In general, the final result should not have more significant figures than the original data from which it was obtained. Thus, if mass of an object is measured to be, say, 4.237 grams, 4 significant figures, and its volume is measured to be 2.51 centimeter cube, then its density, by mere arithmetic division, is 1.68804780876 grams per centimeter cube up to 11 decimal places. It would be clearly absurd and irrelevant to record the calculated value of density to such a precision when the measurements on which the value is based have much less precision. The following rules for arithmetic operations with significant figures ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured values. 1. In multiplication or division, the final result should retain as many significant figures as are there in the original number with the least significant figures. 2. In addition or subtraction, the final result should retain as many decimal places as are there in the number with the least decimal places. The result of computation with approximate numbers, which contain more than one uncertain digit, should be rounded off. The rules for rounding off numbers to the appropriate significant figures are obvious in most cases. A number 2.746 rounded off to 3 significant figures is 2.75, while the number 1.743 would be 1.74. The rule by convention is that the preceding digit is raised by 1 if the insignificant digit to be dropped, the underlined digit in this case, is more than 5, and is left unchanged if the latter is less than 5. But what if the number is 2.745 in which the insignificant digit is 5. Here, the convention is that if the preceding digit is even, the insignificant digit is simply dropped and, if it is odd, the preceding digit is raised by 1. Then, the number 2.745 rounded off to 3 significant figures becomes 1.74. On the other hand, the number 2.735 rounded off to 3 significant figures becomes 1.74 since the preceding digit is odd. In any involved or complex multi-step calculation, you should retain, in intermediate steps, one digit more than the significant digits and round off to proper significant figures at the end of the calculation. Similarly, a number known to be within many significant figures, such as in 2.9979245 into 10 to the power of 8 meters per second for the speed of light in vacuum, is rounded off to an approximate value 3 into 10 to the power of 8 meters per second, which is often employed in computations. Finally, remember that exact numbers that appear in formulae like 2π have a large, infinite, number of significant figures. The value of pi equals 3.141596, is known to a large number of significant figures. You may take the value as 3.142 or 3.14 for pi, with limited number of significant figures as required in specific cases.